Polymorphism may have been asked, "Pray, Mr. Babbage, if you put into the machine wrong figures, will the right answers come out?" I am not able to rightly apprehend the kind of confusion of ideas that could provoke such a question. Charles Babbage 17,911,871 Polymorphism is the third essential feature of an object-oriented programming language, after data abstraction and inheritance. It provides another dimension of separation of interface from implementation, to decouple what from how. Polymorphism allows improved code organization and readability as well as the creation of extensible programs that can be grown not only during the original creation of the project, but also when new features are desired. Encapsulation creates new data types by combining characteristics and behaviors. Implementation hiding separates the interface from the implementation by making the details private. This sort of mechanical organization makes ready sense to someone with a procedural programming background. But polymorphism deals with decoupling in terms of types. In the last chapter, you saw how inheritance allows the treatment of an object as its own type or its base type. This ability is critical because it allows many types derived from the same base type to be treated as if they were one type, and a single piece of code to work on all those different types equally. The polymorphic method call allows one type to express its distinction from another, similar type, as long as they're both derived from the same base type. This distinction is expressed through differences in behavior of the methods that you can call through the base class. In this chapter, you'll learn about polymorphism, also called dynamic binding or late binding or runtime binding, starting from the basics, with simple examples that strip away everything but the polymorphic behavior of the program. Upcasting revisited in the last chapter. You saw how an object can be used as its own type or as an object of its base type. Taking an object reference and treating it as a reference to its base type is called upcasting because of the way inheritance trees are drawn with the base class at the top. You also saw a problem arise, which is embodied in the following example about musical instruments. First, since several examples play notes, we should create a separate note enumeration in a package. Enums were introduced in the initialization cleanup chapter. Here, wind is a type of instrument. Therefore, wind is inherited from instrument. The method music.tune accepts an instrument reference, but also anything derived from instrument. In main, you can see this happening as a wind reference is passed to tune, with no cast necessary. This is acceptably the interface in instrument must exist in wind, because wind is inherited from instrument. Upcasting from wind to instrument may narrow that interface, but it cannot make it anything less than the full interface to instrument. Forgetting the object type music.java might seem strange to you. Why should anyone intentionally forget that could be much more straightforward if tune simply takes a wind reference as its argument? This brings up an essential point. If you did that, you'd need to write a new tune for every type of instrument in your system. Suppose we follow this reasoning and add stringed and brass instruments. This works, but there's a major drawback. You must write type-specific methods for each new instrument class you add. This means more programming in the first place, but it also means that if you want to add a new method like tune or a new type of instrument, you've got a lot of work to do. Add the fact that the compiler won't give you any error messages if you forget to overload one of your methods, and the whole process of working with types becomes unmanageable. Wouldn't it be much nicer if you could just write a single method that takes the base class as its argument, and not any of the specific derived classes? That is, wouldn't it be nice if you could forget that there are derived classes, and write your code to talk only to the base class? That's exactly what polymorphism allows you to do. However, most programmers who come from a procedural programming background have a bit of trouble with the way polymorphism works. Exercise 1. To create a cycle class, with subclasses unicycle, bicycle and tricycle. Demonstrate that an instance of each type can be upcast to cycle via a ride method. The twist: the difficulty with music.java can be seen by running the program. The output is wind.play. This is clearly the desired output, but it doesn't seem to make sense that it would work that way. Look at the tune method public static void tune instrument i/i.play note.midleg. It receives an instrument reference. So how can the compiler possibly know that this instrument reference points to a wind in this case and not a brass or stringed? The compiler can't. To get a deeper understanding of the issue, it's helpful to examine the subject to binding. Method call binding. Connecting a method call to a method body is called binding. When binding is performed before the program is run by the compiler and linker, if there is one, it's called early binding. You might not have heard the term before because it has never been an option with procedural languages. C compilers have only one kind of method call, and that's early binding. Because the compiler cannot know the correct method to call when it has only an instrument reference. The solution is called late binding, which means that the binding occurs at runtime, based on the type of object. Late binding is also called dynamic binding or runtime binding. When a language implements late binding, there must be some mechanism to determine the type of the object at runtime and to call the appropriate method. That is, the compiler still doesn't know the object type, but the method call mechanism finds out and calls the correct method body. The late binding mechanism varies from language to language, but you can imagine that some sort of type information must be installed in the objects. All method binding in Java uses late binding unless the method is static or final. Private methods are implicitly final. This means that ordinarily you don't need to make any decisions about whether late binding will occur. It happens automatically. Why would you declare a method final? As noted in the last chapter, it prevents anyone from overriding that method. Perhaps more important, it effectively turns off dynamic binding, or rather it tells the compiler that dynamic binding isn't necessary. This allows the compiler to generate slightly more efficient code for final method calls. However, in most cases it won't make any overall performance difference in your program, so it's best to only use final as a design decision, and not as an attempt to improve performance. Producing the right behavior. Once you know that all method binding in Java happens polymorphically via late binding, you can write your code to talk to the base class and know that all the derived class cases will work correctly using the same code. Or to put it another way, you send a message to an object and let the object figure out the right thing to do. The classic example in OOP is the shape example. This is commonly used because it is easy to visualize, but unfortunately it can confuse novice programmers into thinking that OOP is just for graphics programming, which is of course not the case. The shape example has a base class called shape and various derived types circle, square, triangle, etc. The reason the example works so well is that it's easy to say a circle is a type of shape and be understood. The inheritance diagram shows the relationships the upcast could occur in a statement as simple as shape s equals new circle. Here, a circle object is created, and the resulting reference is immediately assigned to a shape, which would seem to be an error. Assigning one type to compiler agrees with the statement and doesn't issue an error message. Suppose you call one of the basic class methods that have been overridden in the derived classes s.draw. Again, you might expect that shape's draw is called because this is, after all, a shape reference, so how could the compiler know to do anything else? And yet the proper circle.draw is called because of late binding polymorphism. The following example puts it a slightly different way. First, let's create a reusable library of shape types. The base class shape establishes the common interface to anything inherited from shape, that is, all shapes can be drawn and erased. The derived classes override these definitions to provide unique behavior for each specific type of shape. Random shape generator is a kind of factory that produces a reference to a randomly selected shape object each time you call its next method. Note that the upcasting happens in the return statements, each of which takes a reference to a circle, square, or triangle and sends it out of next as the return type, shape. So whenever you call next, you never get a chance to see what specific type it is, since you always get back a plain shape reference. Main contains an array of shape references filled through calls to randomShapeGenerator.next. At this point you know you have shapes, but you don't know anything more specific than that, and neither does a compiler. However, when you step through this array and call draw for each one, the correct type-specific behavior magically occurs, as you can see from the output when you run the program. The point of creating the shapes randomly is to drive home the understanding that the compiler can have no special knowledge that allows it to make the correct calls at compile time. All the calls to draw must be made through dynamic binding. Exercise 2.1 Add the override annotation to the shapes example. Exercise 3.1 Add a new method in the base class of shapes.java that prints a message, but don't override it in the derived classes. Explain what happens. Now override it in one of the derived classes but not the others, and see what happens. Finally, override it in all the derived classes. This final version overrides print in all classes. Defining print in only the base class results in nothing overrides the basic class definition, so it is used everywhere. Overriding print in circle produces anywhere we override, we use that version, as in circle. Otherwise we use the default basic class version. Exercise 4. To add a new type of shape to shapes.java and verify in main that polymorphism works for your new type as it does in the old types. The other shape definitions are in the same package, so we just add the new shape and override the methods. The code in the for loop is unchanged from the previous example. Exercise 5.1 Starting from exercise 1, add a wheels method in cycle, which polymorphism works. Cycle defines wheels to return 0. In later chapters of TIJ4, You'll learn better ways to specify wheels than using a dummy implementation. Extensibility. Now let's return to the musical instrument example. Because of polymorphism, you can add as many new types as you want to the system without changing the tune method. In a well-designed loop program, most or all of your methods will follow the model of tune and communicate only with the basic class interface. Such a program is extensible because you can add new functionality by inheriting new data types from the common base class. The methods that manipulate the basic class interface will not need to be changed at all to accommodate the new classes. Consider what happens if you take the instrument example and add more methods in the base class and a number of new classes. Here's the diagram. All these new classes work correctly with the old, unchanged tune method. Even if tune is in a separate file and new methods are added to the interface of instrument, tune will still work correctly, even without recompiling it. Here is the implementation of the diagram. The new methods are what, which returns a string reference with a description of the class, and adjust, which provides some way to adjust each instrument. In main, when you place something inside the orchestra array, you automatically upcast the instrument. You can see that the tune method is blissfully ignorant of all the code changes that have happened around it, and yet it works correctly. This is exactly what polymorphism is supposed to provide. Changes in your code don't cause damage to parts of the program that should not be affected. Put another way, polymorphism is an important technique for the programmer to separate the things that change from the things that stay the same. Exercise 6.1. Change music3.java so that what becomes the root object method toString. Try printing the instrument objects using system.out.println without any casting. Exercise 7. To add a new type of instrument to music3.java and verify that polymorphism works for your new type. Exercise 8. To modify music3.java so that it randomly creates instrument objects the way shapes.java does. A generator produces a new value each time you call it, though you don't give it any parameters. The generator instant produces a random value within the array between 0 inclusive and the value of the argument exclusive. Managing the case statement with a random generator can be a raw. However, features of the class object enable us to index an array that itself generates various instruments, as in this more elegant solution. The class syntax in the array definition produces references to class objects for each type of instrument. Class.new instance creates an object of the class it is called for, but it can throw exceptions. Here, we create and throw an onto-me exception for this programming error, so your code doesn't have to catch such exceptions. You can embed the cause of an error inside a thrown exception. Cover exceptions in detail in the chapter Error Handling with Exceptions. The benefit of this design is that you can add a new type to the system by only adding it to the class array. The rest of the code takes care of itself. Exercise 9.3. Create an inheritance hierarchy of rodent, mouse, gerbil, hamster, etc. in the base class. Provide methods that are common to all rodents, and override these in the derived classes to perform different behaviors depending on the specific type of rodent. Create an array of rodent, fill it with different specific types of rodents, and call your basic class methods to see what happens. Exercise 10.3. Create a base class with two methods. In the first method, call the second method. Inherit a class and override the second method. Create an object of the derived class, upcast it to the base type, and call the first method. Explain what happens. The first method isn't overridden, but it calls the second method, which is? Java always uses the most derived method for the object type. This is very powerful and may surprise the unaware. The template method design pattern makes heavy use of polymorphism. See Thinking in Patterns with Java at www.mindview.net. Pitfall: overriding private methods. Here's something you might innocently try to do. You might reasonably expect the output to be public F, but a private method is automatically final, and is also hidden from the derived class. So derived F in this case is a brand new method. It's not even overloaded, since the basic class version of F isn't visible in derived. The result of this is that only non-private methods may be overridden, but you should watch out for the appearance of overriding private methods, which generates no compiler warnings, but doesn't do what you might expect. To be clear, you should use a different name from a private basic class method in your derived class. Pitfall: fields and static methods. Once you learn about polymorphism, you can begin to think that everything happens polymorphically. However, only ordinary method calls can be polymorphic. For example, if you access a field directly, that access will be resolved at compile time, as the following example demonstrates. 1. Thanks to Randy Nichols for asking this question. When a subobject is upcast to a superreference, any field accesses are resolved by the compiler, and are thus not polymorphic. In this example, different storage is allocated for super.field and sub.field. Thus, sub actually contains two fields called field its own and the one that it gets from super. However, the super version is not the default that is produced when you refer to field in sub. In order to get the super field, you must explicitly say super.field. Although this seems like it could be a confusing issue, in practice it virtually never comes up. For one thing, you'll generally make all fields private, and so you won't access them directly, but only as side effects of calling methods. In addition, you probably won't give the same name to a basic class field and a derived class field, because it's confusing. If a method is static, it doesn't behave polymorphically, doesn't handle every case, as you will see in the next section. Exercise 11.1 Add class pickle to sandwich.java. Notice that pickle appears in the correct order, after the other member objects. Inheritance and cleanup. When using composition and inheritance to create a new class, most of the time you won't have to worry about cleaning up. Subobjects can usually be left to the garbage collector. If you do have cleanup issues, you must be diligent and create a dispose method, the name I have chosen to use here. You may come up with something better for your new class. And with inheritance, you must override dispose in the derived class if you have any special cleanup that must happen as part of garbage collection. When you override dispose in an inherited class, it's important to remember to call the basic class version of dispose, since otherwise the basic class cleanup will not happen. The following example demonstrates this. Each class in the hierarchy also contains a member objects of types characteristic and description, which must also be disposed. The order of disposal should be the reverse of the order of initialization, in case one subobject is dependent on another. For fields, this means the reverse of the order of declaration, since fields are initialized in declaration order. For base classes following the form that's used in C for destructors, you should perform the derived class cleanup first, then the basic class cleanup. That's because the derived class cleanup could call some methods in the base class that require the basic class components to be alive, so you must not destroy them prematurely. From the output you can see that all parts of the frog object are disposed in reverse order of creation. From this example, you can see that although you don't always need to perform cleanup, when you do, the process requires care and awareness. Exercise 12.3 Modify exercise 9 so that it demonstrates the order of initialization of the base classes and derived classes. Now add member objects to both the base and derived classes and show the order in which their initialization occurs during construction. We initialize the base class first, starting with the member objects in order of definition, then the derived class, starting with its member objects. Also note that in the above example, a frog object owns its member objects. It creates them, and it knows how long they should live as long as the frog does, so it knows when to dispose the member objects. However, if one of these member objects is shared with one or more other objects, the problem becomes more complex, and you cannot simply assume that you can call dispose. In this case, reference counting may be necessary to keep track of the number of objects that are still accessing a shared object. Here's what it looks like. The static long counter keeps track of the number of instances of shared that are created, and it also provides a value for id. The type of counter is long rather than int. To prevent overflow, this is just good practice. Overflowing such a counter is not likely to happen in any of the examples in this book. The id is final because we do not expect it to change its value during the lifetime of the object. When you attach a shared object to your class, you must remember to call a ref, but the dispose method will keep track of the reference count and decide when to actually perform the cleanup. This technique requires extra diligence to use, but if you are sharing objects that require cleanup, you don't have much choice. Exercise 13.3 Add a finalize method to reference accounting.java to verify the termination condition. See the initialization cleanup chapter. Exercise 14.4 Modify exercise 12 so that one of the member objects is any other methods in this class. The only safe methods to call inside a constructor are those that are final in the base class. This also applies to private methods, which are automatically final. These cannot be overridden and thus cannot produce this kind of surprise. You may not always be able to follow this guideline, but it's something to strive towards. Exercise 15 to add a rectangular glyph to polyconstructors.java and demonstrate the problem described in this section. This section shows how polymorphism calls the most derived method, even before completely initializing the object. During construction, you see output of area equals 0 because the basic class constructor calls draw, though this isn't obvious in the code. Covariant return types Java SE5 adds covariant return types, which means that an overridden method in a derived class can return a type derived from the type returned by the basic class method. The key difference between Java SE5 and earlier versions of Java is that the earlier versions would force the overridden version of process to return grain, rather than wheat, even though wheat is derived from grain and thus is still a legitimate return type. Covariant return types allow the more specific wheat return type. Designing with inheritance. Once you learn about polymorphism, it can seem that everything ought to be inherited, because polymorphism is such a clever tool. This can burden your designs. In fact, if you choose inheritance first when you're using an existing class to make a new class, things can become needlessly complicated. A better approach is to choose composition first, especially when it's not obvious which one you should use. Composition does not force a design into an inheritance hierarchy. But composition is also more flexible since it's possible to dynamically choose a type and thus behavior when using composition, whereas inheritance requires an exact type to be known at compile time. The following example illustrates this. A stage object contains a reference to an actor, which is initialized to a happy actor object. This means perform played produces a particular behavior. But since a reference can be rebound to a different object at runtime, a reference for a said actor object can be substituted in actor, and then the behavior produced by perform play changes. Thus you gain dynamic flexibility at runtime. This is also called the state pattern. See Thinking in Patterns with Java at www.mindview.com. In contrast, you can't decide to inherit differently at runtime. That must be completely determined at compile time. A general guideline is use inheritance to express differences in behavior, and fields to express variations in state. In the preceding example, both are used. Two different classes are inherited to express the difference in the act method, and state uses composition to allow its state to be changed. In this case, that change in state happens to produce a change in behavior. Exercise 16.3. Following the example in transmogrify.java, create a Starship class containing an alert status reference that can indicate 3 different states. Include methods to change the states. This is an example of the state design pattern, wherein the object's behavior is state-dependent. The 3 states of an alert status object, to which the Starship class holds a reference, represent behaviors of the Starship. You switch the set status reference from one state to another to change the behavior of the Starship. Substitution versus extension. It would seem that the cleanest way to create an inheritance hierarchy is to take the pure approach. That is, only methods that have been established in the base class are overridden in the derived class. As seen in this diagram, this can be called a pure is a relationship, because the interface of a class establishes what it is. Inheritance guarantees that any derived class will have the interface of the base class and nothing less. If you follow this diagram, derived classes will also have no more than the basic class interface. This can be thought of as pure substitution, because derived class objects can be perfectly substituted for the base class, and you never need to know any extra information about the subclasses when you're using them. That is, the base class can receive any message you can send to the derived class, because the two have exactly the same interface. All you need to do is upcast from the derived class and never look back to see what exact type of object you're dealing with. Everything is handled through polymorphism. When you see it this way, it seems like a pure is a relationship is the only sensible way to do things, and any other design indicates muddled thinking and is by definition broken. This too is a trap. As soon as you start thinking this way, you'll turn around and discover that extending the interface, which, unfortunately, the keyword extend seems to encourage, is the perfect solution to a particular problem. This can be termed an is-like-o relationship, because the derived class is like the base class. It has the same fundamental interface, but it has other features that require additional methods to implement. While this is also a useful and sensible approach depending on the situation, it has a drawback. The extended part of the interface in the derived class is not available from the base class, so once you upcast, you can't call the new methods. If you're not upcasting in this case, it won't bother you, but often you'll get into a situation in which you need to rediscover the exact type of the object so you can access the extended methods of that type. The following section shows how this is done. Downcasting and runtime type information. Since you lose the specific type information via an upcast moving up the inheritance hierarchy, it makes sense that to retrieve the type information, that is, to move back down the inheritance hierarchy, you use a downcast. However, you know an upcast is always safe, because the base class cannot have a bigger interface than the derived class. Therefore, every message you send through the base class interface is guaranteed to be accepted. But with a downcast, you don't really know that a shape, for example, is actually a circle. It could instead be a triangle or square or some other type. To solve this problem, there must be some way to guarantee that a downcast is correct, so that you won't accidentally cast to the wrong type and then send a message that the object can't accept. This would be quite unsafe. In some languages like C, you must perform a special operation in order to get a type a safe downcast, but in Java, every cast is checked. So even though it looks like you're just performing an ordinary parenthesized cast, at runtime this cast is checked to ensure that it is in fact the type you think it is. If it isn't, you get a class cast exception. This act of checking types at runtime is called runtime type identification T. The following example demonstrates the behavior of T as in the previous diagram. More useful extends the interface of useful. But since it's inherited, it can also be upcast to a useful. You can see this happening in the initialization of the array X in main. Since both objects in the array are of class useful, you can send the F and G methods to both. Compile a time error message. If you want to access the extended interface of a more useful object, you can try to downcast. If it's the correct type, it will be successful. Otherwise, you'll get a class cast exception. You don't need to write any special code for this exception, since it indicates a program or error that could happen anywhere in a program. The throws exception comment tag tells this book's build system to expect this program to throw an exception when it executes. There's more to T than a simple cast. For example, there's a way to see what type you're dealing with before you try to downcast it. All of the type information chapter is devoted to the study of different aspects of Java runtime type identification. Exercise 17. 2. Using the cycle hierarchy from Exercise 1, add a balance method to unicycle and bicycle, but not to tricycle. Create instances of all three types and upcast them to an array of cycle. Try to call balance on each element of the array and observe the results. Downcast and call balance and observe what happens. Summary: polymorphism means different forms. In object-oriented programming, you have the same interface from the base class, and different forms using that interface the different versions of the dynamically bound methods. You've seen in this chapter that it's impossible to understand, or even create, an example of polymorphism without using data abstraction and inheritance. Polymorphism is a feature that cannot be viewed in isolation like a switch statement can, for example, but instead works only in concert, as part of the larger picture of class relationships. To use polymorphism and thus object-oriented techniques effectively in your programs, you must expand your view of programming to include not just members and messages of an individual class, but also the commonality among classes and their relationships with each other. Although this requires significant effort, it's a worth the struggle. The results are faster program development, better code organization, extensible programs, and easier code maintenance. Solutions to selected exercises can be found in the electronic document The Thinking in Java Annotated Solution Guide, available for sale from www.mindview.net.